Hello everyone, welcome to another episode of Math-321. So today we're going to continue Investigation 27, which is normal subgroups and quotient groups. Okay, so let's recall what we did last time. So if we let G be a group with the operation written multiplicatively and then H a subgroup of G, and we let little g be an element of G, remember that the left coset of H in G containing little g is the set little g H, which just consists of little g times H for all of the little h's in big H. So it's just what it looks like. You multiply that element G times everything that is in the subgroup H. Then last time we said that we were going to denote by G mod H. So this thing here is read G mod H, the collection of all distinct left cosets of the subgroup H in the group G. And then hopefully, possibly today, it might become clear exactly why we read it as G mod H. So we want to understand when this set G mod H is actually a group. And last time we looked at some examples where it was and where it wasn't. So to identify a group structure, we need an operation. So there's a natural way to do an operation on these left cosets. So for any two left cosets, AH and BH in G mod H, we can define the product of AH, BH like this. You just do the product of A and B, and then you use that coset AB, H. So in the activity that we did at the end of last time, we saw that for one subgroup H, we had this condition. We had AH equals HA for all of the elements A in G. And we saw also that the coset multiplication operation was well defined on the cosets of H. And then we also saw that there was another subgroup in that group called K, and we had that AK did not always equal KA. And we saw that the coset operation for those cosets was not well defined. So we're going to continue on with that theme and look a little more deeply at that concept. Okay, so for this activity here, there's a note here before we begin. So note that just because AH equals HA, that does not necessarily imply that that A times little h equals little HA for all of the little h's in the subgroup H. So rather what it does imply is that for all of the elements in that subgroup H, there exists some other element of that subgroup such that AH would equal H prime A. Okay, and so you can think about this as being similar to something that we talked about when we were doing symmetries of polygons. You know that when you do like a rotation of a square and the square lands back on itself, that doesn't mean that every point in the square landed back on itself. That's not the case at all. It's just that the entire square as a whole is going to be equal before and after a rotation or a reflection. But not every point in that square is going to end up in the same place. So it's the same concept here. So anyway, it's precisely when we have this condition that AH equals HA, that is when G mod H will be a group. And so this next activity here is going to help us show that that is the case. So go ahead and pause the video and give this activity a try, and then we'll go over it. Okay, so let's look at this activity. So let G be a group and let H be a subgroup of G such that GH equals HG for all G in G. Let A prime, B, and B prime be elements of G with AH equal to A prime H and BH equal to B prime H. So first of all, we have to explain why there must be elements HA and HB in H such that A equals A prime HA and B equals B prime HB. Okay, so this is not too bad. So first, recall that A is going to be in AH and B is going to be in BH, and that's easy to see if you remember that the identity element is an element of H. So that can be the element that we multiply by A and B to get them into AH and BH. Since AH equals A prime H, that means that A is also going to be in A prime H, and then likewise B is also going to be in B prime H. So that means if A is in A prime H, well then A must equal A prime times some element of H, and we're just calling that HA, and then likewise for B, it's like this. For some HA and HB in H. Oops. Okay, so for part B, what you need to take note of is the following. Since HB prime equals B prime H, and that is just coming from this equation that we were given in the activity that GH equals HG. So all the left cosets are the same as the right cosets. And let's see, HA is an element of H. So that means that HAB prime is in HB prime. So we also have that HAB prime is going to be an element of B prime H, since HB prime and B prime H are the same thing. So it also has to be in that one. So if it's going to be in there, there must be some element of H that let it be in there. So we're just calling that H prime. So HAB prime has to equal B prime H prime for some H prime in H. Okay, so that is part B. Okay, so for part C, use the previous two results to show that AB is an element of A prime B prime H. What does that tell us about the relationship between ABH and A prime B prime H? Okay, so the previous two results were the following. So these were A equals A prime HA and B equals B prime HB, and the other one was HA B prime equals B prime H prime for some HA HB and H prime, which are elements of H. Okay, so how are we going to combine these? So we need to show that AB is an element of A prime B prime H. So let's look at what AB is. So then AB, so we have equations for A and B, so I'm just going to multiply those together. So this will be A prime HA, B prime HB. And now what you see is that we have this part in the middle here that is HAB prime. So I'm going to substitute for that and get A prime, B prime, H prime, HB. Okay, and now what you want to notice is that, so that became that. So now what you want to notice is that H prime HB is an element of H. So this is in A prime B prime H. Because H prime HB is in H, and that's because H is, of course, closed under multiplication because it's a subgroup. Okay. So what I can say from this is that AB is in A prime B prime H, and since cosets are either disjoint or they are identical, and that's because the cosets partition the group, that means that ABH must equal A prime B prime H. Okay, so part D, explain why the multiplication operation on left cosets is well defined on G mod H. So what we've shown here is the following. We've shown that if we represent a left coset using two different elements, A and A prime, which are both in that coset, and the same for B, if we represent BH by two different representative elements, B and B prime, we still get the same thing when we multiply them together. So AH, BH, which is ABH, is going to give us the same thing as doing A prime B prime or A prime H, B prime H. And so that shows us that this operation is well defined. So it doesn't matter what element in the coset we use to represent it or to write it, we will get the same product no matter what, and you need your operation to be well defined in order to be able to do anything mathematical with it. Okay, so this brings us to the concept of normal subgroups. So definition 27.4, let G be a group. A subgroup N of G is normal in G, or is a normal subgroup of G, if AN equals NA for all A in G. So if all the left and the right cosets of N are the same, then the subgroup is called normal. And we're calling it N for short because it's N for normal, obviously. Okay, so there's some notation associated with this, and I think this notation makes more sense if you also know the notation for a subgroup. So we had not been using this notation previously, but this is a notation that exists for subgroups. So this H less than or equal to G actually stands for H is a subgroup of G, and then just using the less than symbol, that means H is a proper subgroup of G. So by proper, it means it's a subgroup and it's not equal to G. And then finally, that brings us, hopefully this notation then looks a little less strange in context. It's H and then the little triangle G. That means H is a normal subgroup of G. So we can simplify this process of checking whether all the left and right cosets are the same by multiplying both sides of this AN equals NA equation. If we multiply them on the right by A inverse, then we get this equation right here. So AN A inverse equals N. So that is an easier way to check. And then the next theorem is showing us that there's actually an even easier way than that. So you know that normally when you're checking that two sets are equal, you have to show that they are each a subset of each other. But this next theorem is telling us that we only have to check the subset relationship in one direction. So that's quite nice. So theorem 27.5, let G be a group and N a subgroup of G. Then N is normal in G if and only if AN A inverse is a subset of N for all A in G, where they just define this notation here, AN A inverse, that equals exactly what it looks like it equals. It's just a little n A inverse for all of the little n's in big N. So we're going to go ahead and prove this on the next slide. Okay, so here is the proof of the theorem. It's not a complete proof, but it's the hard parts. So I put the theorem up there in the corner for you. So this is an if and only if statement that is in the theorem. So to prove an if and only if statement, you have to prove that both parts imply each other. So we need to show part one here, N is normal in G implies that AN A inverse is a subset of N for all A in G. And then the other way around, part two, we have to show that AN A inverse being a subset of N for all A in G, that would imply that N is normal in G. Okay, so the first one there is actually an exercise that is in the homework section, which I am thinking of assigning to you. So I'm going to leave that out. And then part two, which is actually the harder part. So for that part, we're proving an if-then statement. So we're going to assume the if part. So assume that AN A inverse is a subset of N for all A in G. And then what we need to show is that that means that N is normal. So in other words, we need to show that AN equals NA for all A in G. So in order to show that those two things are equal, they are both sets. So we're going to do the standard approach when you're proving that two sets are equal, which is to show that they are subsets of each other. So we're going to show that AN is a subset of NA and that NA is a subset of AN for all of the A's in G. Okay, so that's what the two paragraphs here are for. So first of all, let A be an element of G and let let AN, little n, be an element of A big N. So recall that to show that something is a subset, you have to show that if any element is in the left side, like this AN part, then that element will also be in the right side, right there. So that's what we're doing here. We're going ahead and assuming that we have an element which is in the left side. So we have A little n being an element of A big N. So by our assumption, we have assumed that AN A inverse is a subset of N. So that would mean that A little n A inverse is equal to N prime for some N prime in N. Okay, so because A little n A inverse is in this thing here, then it must also be in this thing here because they are subsets. Okay, so then we can take this equation right here, that AN A inverse equals N prime, and we can just multiply both sides on the right by A. And then what's going to happen is it'll cancel down to this. So AN will equal N prime A. So that would tell us that AN is an element of big N A. And so by that, all that we've just done in that paragraph, that shows that A big N is a subset of big N A. Okay, so then for the other way around, so that was this part. and then this one is this part down here. Okay, so we're going to let A be an element of G, and we're going to suppose that we have something in the left side of the subset we're trying to show. So we're showing that, or sorry, we're assuming that little n(a) is an element of big N(a), and then we're going to show that little n(a) also has to be an element of A times big N. So again, by our assumption, we assumed that A in A inverse is a subset of N for all A in G. Now, notice that we did assume that for all A's in G. So A inverse is also an element of G. So we could just as easily say the same thing about A inverse. And to do that, what it would look like is this. So A inverse N times A inverse inverse is a subset of N. So that's making the same statement, but for A inverse instead of A. And that can be simplified. Okay, sorry, I just had to pause the recording because my cat is trying to obstruct you from learning math. He is not a math fan. Okay, so anyway, I think we simplified down to this statement here, that A inverse NA is a subset of N. So what we can write from that is that A inverse little na is equal to n prime for some n prime in N. And so if we just multiply both sides of that on the left by A, then it cancels down to this equation right here, this one. So NA will be equal to A n prime, and that tells us that NA is also an element of A capital N. And so what we've shown in this paragraph right here, we started off by assuming we had something in NA, and then we showed that thing was also in AN. So that means that NA is a subset of AN. Okay, so we've shown that AN and NA are subsets of each other, and that means that they must be equal. Okay, so that is this proof, and again, part 1 is an exercise. Okay, so now let's do an activity where you actually have to use Theorem 27.5, or it's probably at least easier to use it. So for each part below, decide if the given subgroup N is a normal subgroup of the group G, and then use that theorem if you would like to. And note that for A and B, the groups do use addition, not multiplication. So if you're thinking about how you're going to write this A in A inverse thing, you would write that as A plus N minus A. Okay, so keep that in mind and go ahead and pause the video and try this, and then we'll go over it. Okay, so let's go ahead and go over part A here. So we're doing this one. And then, so let's think for a second about what this normal subgroup, what this potentially normal subgroup actually is. So what is N? So the subgroup generated by the congruence class of 2 would be the following. So it'll be the identity, and then 2, and then 2 times 2, which is 4, and then 3 times 2, which is 6, and then after that it would be 4 times 2, which is 8, so that's the identity again. So that is our subgroup. So what we need to know is A plus N minus A subset of N for all A in the group. So this one is actually really easy because this group is abelian. Let me just say that. So since Z8 is abelian, A plus N minus A will just equal N. Or maybe we could say it like this, N plus A minus A, so that's N, which is of course a subset of itself. So N is normal. Okay, so that is part A. Okay, so for part B, so this one is kind of equally easy because the group is abelian actually. But let me just write out actually what the group is first of all, so you know what we're even talking about here. So that is going to be, let's see, so it's all the multiples of 5, the integer multiples of 5. So there'll be 0, 5, 10, and so on. And then in the other direction, there'll be -5, -10, and so on. So yes, in this case, we will also have that A plus N minus N is equal to N plus A minus A, which is just N, which is a subset of N, of course, because the group is abelian. So not actually very interesting. So yeah, n is normal. Okay, let's look at part C. Okay, so let's look at part C here and see if it's any more interesting than these other ones. So I don't know how well you guys remember this from other times that we've talked about the symmetric group, but this subgroup that's generated by 1, 2, 3, that is just the identity, and then it's 1, 2, 3, and then it's 1, 3, 2, and then that's it. So that's the n in question here, and then we want to see is A inverse, is that a subset of n for all a's in the group? So there's only 6 elements in this group, and we already have 3 of them in our normal subgroup, so we don't need to check the ones that are already in there, because if something is already in, then doing A inverse will just be n again. So we don't need to check the a's that are already in. So let's check the other ones. So let's check when a is equal to 1, 2. So let's just see. So what is A inverse in this case? So this is going to be 1, 2 times these things that are in the set. So 1, 2, 3, and then 1, 3, 2, and then we'll do 1, 2 inverse, which is actually just 1, 2 again, because it's a transposition, its inverse is the same. Okay, so this is going to be, so this will be 1, 2, and then I, and then 1, 2 again, and then this will be 1, 2, and then 1, 2, 3, and then 1, 2 again, and then the last one will be 1, 2, and then 1, 3, 2, and then 1, 2 again. So what are these? So the first one I think is just the identity. And the second one is going to be, okay, so let's see, where does 1 get moved to? So first it gets moved to 2, and then 2 goes to 3, and then 3 goes nowhere, so it gets moved to 3. And then where does 3 get moved to? Let's see, so nowhere, and then back to 1, and then to 2. So that is that one. And then the last one is going to be, let's see, 1 gets moved to 2, and then 2 goes back to 1, and then 1 goes to 2. So in the last one here, 1 is going to 2. And then where does 2 get moved to? So 2 goes to 1, and then 1 goes to 3, and then 3 goes nowhere. So that goes to 3. Okay, so this is n. And then we would want to check the others as well. I think this is going to be like fairly time consuming. So you'd want to check these other 2, 1, 3. I do believe that they're all going to be give you n again, I think, but you can check these yourself and see that you get n again. Okay, I just don't want to make the video go like super long, but that's how you would do it. Okay, so let's talk a little more about quotient groups. So let G be a group and let n be a normal subgroup of G. So recall that the operation on G mod n, remember that's that set of left cosets, although actually since n is normal, they're both the left and the right cosets. Recall that the operation on G mod n, defined as an times bn equals abn for all a, b, and g, that is well defined when n is a normal subgroup of G. We actually proved that. It is natural to ask what kind of structure this operation imposes on G mod n. In other words, does it impose a group structure? So in this activity here, we're going to show that it does. So go ahead and pause the activity, pause the video and try this activity, and then we'll go over it. Okay, so let's go over this activity. So there is an identity element in G mod n, and what is it? And verify your answer. Okay, so basically we're looking for the following. So we're looking for an element G in G, such that whenever we use the coset of G, so whenever we use Gn, and we multiply that by another coset, say an, that will give us just an again for all a in G. And we also need the following, I should say also that an has to be able to be multiplied on the other side by Gn as well, for all A in G. So hopefully it's not too hard for you to realize what this G should actually be. So let little g be E, and that by E I mean the identity. I can't remember if we said that was the identity in this group. So then if that is the case, then we'll have the following. So for all elements A of G, then when we do En times An, the way the operation works, remember, is that you do the two elements together like that, times n, and that is actually just going to be An. And then if we do it the other way around, An first and En second, we'll get the same thing. So this will be Ae times n, and that will also just be An. So En, which is actually just n, is the identity for G mod n. Okay, so that's the coset that whenever you whenever you multiply by it, it just does nothing. It just leaves you with whatever you multiplied by. Okay, part B, prove that the operation is associative on G mod n. So we're gonna let let's take three cosets that are in G mod n. So let An be n and Cn be in G mod n, or we could have just said let A, B, and C be in G, and then these would be in G mod n. So we need to show the following. So we need to show that we can start with, let's see, how am I going to write this? An times Bn. I'll do it like, well, maybe not with square brackets because we have a different meaning for that, right? So I'll put those two together. And then Cn, we need to show that we can multiply An and Bn first, and that it's the same as if we multiply by Bn and Cn first. So let me see if I can do this. So this is going to be, so this will be Abn times Cn, and then that is going to be, maybe I should put these in parentheses. That is going to be AB times Cn. And so because the group operation itself, the group G, that operation is associative because it's a group, that means that we can write this as just ABC times n. And then we can split this up differently. So let me see, how do I do this? Put B and C together, like that. And then I can split back out like this, An like that. And then over here I'm going to have B and C still together. And then let's see, An, okay, and then I'm going to have Bn and Cn. Okay, and then, oh, then I'm done, I think. That's done, right? Okay, so it all goes back to the fact that G's operation is associative. It doesn't matter whether you do the AB part first or the BC part first. That's what allows this operation on G mod n to also be associative. Okay, so let's look at part C, prove that G mod n contains an inverse for each of its elements. So just like it wasn't very hard on part A to guess that the identity would be the identity times n, it's going to be the same way this time. Like if you want the inverse of An, it's going to be A inverse n. Okay, so let me just show that. So let An be an element of G mod n. Then A inverse n is also an element of G mod n, because if A is an element of G, then A inverse is an element of G. Oops, I should actually write A inverse, I guess. Okay. And we can see the following. So if I do An times A inverse n, then I'm going to get A inverse n, which is going to be En, which is going to be n. So that is the identity. Remember, when you multiply two inverses, you need to get the identity. Okay, and then also the following. So if I do it in the other order, then I'm going to get A inverse A times n, and that will be En, and that will just be n, and that is the identity. So I'll just point that out, since n is the identity. This means, oops, that's not an I. This means that A inverse n is the inverse of an. Okay, so that wasn't very hard. And then finally, part D, explain why G mod n is a group under the operation. So I think it already stated in the previous material that the group operation is closed. So we verified closed, not ourselves, but we were told it was closed. And then we verified that we have the identity, and then we verified inverses, and we also verified associativity. So those are the 4 things that you need to be a group. So G mod n is a group. Okay, so this brings us to the definition of a quotient group. So the formal definition here, I think we talked about it a little bit, but definition 27.8, let G be a group and n a normal subgroup of G. The quotient group, also known as the factor group of G by n, is the group G mod n equals, and then it's just all of the cosets where the little a part there is an element of G, with the operation an times bn equals abn for all ab in G. Okay, so great. This thing that we've been talking about as a group, it really is a group, and we have proven it. So next is an activity for you to try. Since these are groups, you can construct operation tables for them. So go ahead and give that a try, pause the video, and then we'll go over it. Okay, so let's go over part A here. So let's see. Z8, so that's just 0 through 7, the congruence classes for those. And then n is generated by the congruence class of 2. So let's just write out what n actually is. So it's going to contain 0, and then 2, and then also 4, and then 6. So those are all the integer multiples of 2. So that's what n is. And then we need to figure out what is actually G mod n. So remember, G mod n is going to be the all of the cosets, the left cosets. But in this case, actually, our operation is additive. It's not multiplication. So this is going to be all of the cosets that are going to look like a plus n for some element a in the group. So in fact, what do we get here? So we get n itself. That's obviously one of them. And then what are the others? So what are the things that we could add to n, or that we could add to every multiple, or sorry, every element of n? So actually the only one that you really need is this one. So you need 1 plus n. And then, so that would give you, so this would be, so just adding 1 to all of the elements of n, you get 1, you get 3, and then you get 5, oops, and then you get 7. And so you can see that those 2 cosets right there, they do cover all of G. So once you've covered all of G, that's all your cosets, because the cosets form a partition of G. So these are the only 2 cosets, and so our operation table is not going to be very complicated. So here's our operation, and do note that here the operation, it is going to be addition. So maybe let me just make a little note about that. So if we're doing, how can I say this? Like, the cosets look like this, right? So you're not multiplying them, you're going to be adding them. So your addition of 2 cosets is just going to be like a plus b and then plus n, like that. So it's the additive notation. Okay, so our only 2 here are n, and then 1 plus n. So it's a very small table. Okay, so what do I get if I add n plus n? So that is just going to be n again. Okay, if you think about adding any of the elements in n to the elements in n, you are still getting all of the elements in n again. And then what if I do, so if I do n plus 1 plus n, so that is actually just going to be 1 plus n again. And then if I do it the other way around, so if I do 1 plus n, this group is abelian, so it really doesn't matter what order you do it in. This is just going to give you 1 plus n again. And then since we know this is a group, and Sudoku rules still apply to group operation tables, so we know this has to be n. But hopefully you also understand that you can see that by doing 1 plus n, and then 1 plus n again, and then that would actually give you 2 plus n. And so what is 2 plus n? Well, 2 is actually an element of n. So remember that you can represent the same coset using any element that is in the coset. So this really is just n again, because we used an element for the representative that is in the coset. Or another way to think of it is if you just take all the elements of n and then you add 2 to them, you are just going to get n again. So that's n. Right, so that's our operation table. It's a very kind of small and cute one. So let's do part B here. So our group is the integers, and our n is the group generated by, or the subgroup generated by 5. So here n is going to be the following. So it's going to start with -10, -5, 0, 5, 10. So it's all the integer multiples of 5. So that's our n. And so what is actually going to be in G mod n? So obviously n is going to be in there. And then what else needs to be in there? So there's going to be 1 plus n, there's going to be 2 plus n, there's going to be 3 plus n, and there's going to be 4 plus n. And then if you try to do 5 plus n, that'll just be n again. So those are the only 4 that you need, or sorry, the only 5 cosets that you need to partition the integers. So that is all of them. And so for our group operation table here, it's only going to have 5 rows and columns. So I'm going to have n, 1 plus n, 2 plus n, 3 plus n, and 4 plus n. Okay, and then on the other side, of course, I'm going to have the same thing. Okay, and then just to remind you, the group operation here, it's addition, not multiplication. Okay, so if I add n plus n, what am I going to get? If I add anything in n to anything else in n, I'm still going to be in n. So this is n again. And then if I do n plus 1 plus n, that is going to be 1 plus n again. If I do n plus 2 plus n, that's going to be 2 plus n again. You know, we already talked about the fact that n is always the identity element, so it shouldn't be too surprising that you're just filling in these using the n as the identity. So these are just copied over like you do an operation table whenever you're using the identity. Okay, so then the rest of them are a little bit more complicated, but not very. So let's see, 1 plus n plus 1 plus n, that is going to be 2 plus n. 2 plus n plus 1 plus n is going to be 3 plus n, and then same deal down here, this is going to be 4 plus n. Now what happens if we do 4 plus n plus 1 plus n? So that's a little more interesting, right? That's 5 plus n. But what is 5 plus n? 5 is an element that's already in n, and that's not one of our cosets that we listed. So this one is actually n. So that's interesting. And then we can come through and do these the same way. So it's going to be 4 plus n. The next one would be 5 plus n, but that's just n. And then down here, this would be 6 plus n. But if I do 6 plus anything that's in n, I'm going to get what I'm going to find is this is the same coset as 1 plus n. So if you add 6 to everything that's in n, and then you look at what you've got, so maybe I'll just do like a little sidebar. Let me show you this. So 6 plus n. So if I just go through n and I add 6 to all of the elements, I'm going to get, let's see, so ... and then the first one would be -4, and then 1, and then 0 plus 6 is 6, 5 plus 6 is 11, 10 plus 6 is 16, ... Look at that for a second and convince yourself that that is the exact same thing as 1 plus n, because it's the same as just taking the elements from n and adding 1 to all of them. Okay, so that is actually the same as 1 plus n. Okay, and then I can come down and do the same thing over here. So this is 4, and then this would be 5, but 5 goes away, so that's just n. And then this is going to be 6 plus n again, but 6 plus n is 1 plus n. And then same deal down here, I would get 7 plus n, but 7 plus n is the same as 2 plus n. Okay, and then over here, this would be 5, but that's just n. And then this would be 6, but that's the same as 1 plus n. And then this one would be 7 plus n, but that's the same as 2 plus n. And then this one would be 8 plus n, but 8 plus n is the same as 3 plus n. So if you look at this table for long enough and you think about the things that we've just been saying, like for example that 7 plus n is the same as 2 plus n, I think it is not too hard to convince yourself that this is actually essentially the same as the following. It's the same as Z5, right? Because n, what is n? N actually is this. It's the congruence class of 5, mod 5. And then 1 plus n actually is the congruence class of 1, mod 5. I'm going to put the little 5 subscripts here to make it more convincing. And then 2 plus n actually is the same as 2 mod 5, the congruence class. Okay, and then etc. And this is the exact same operation table that you get in Z5. So this is actually explains why G mod n is read aloud as G mod n. It's read aloud as G mod n because what you can see is that Z mod 5Z is actually Z5. And so that's why we read that aloud like that, because it all goes back to the modulus operation. So that modulus, those modulo groups like Z5 are actually identical to groups like Z mod 5Z. So anyway, that's an interesting point there. We might come back and revisit that in some detail later on. Okay, so let's go over part C here. So we are using the dihedral group of the symmetries of the square. So let me just remind you about how the dihedral group works. So this is symmetries of the square. And so D4, you can write its elements this way. I think there's actually like a couple of different ways to do it, but let me just do it this way. So I'm going to have I, and then R squared, and then R cubed. So these are the rotations. And then for the reflections, there's little r, and then you can write on the little r on either side of the big R's and get all of the group elements. But I think for the purposes of this activity, I want to write the little r on the left, like this. So little r squared, and then little r cubed. And like I said, if you wrote big R squared, little r, or big R cubed, little r, that would still be all of the elements of this group. So the first 4 are the rotations, and then the last 4 are the reflections. And then, of course, big R itself is the 90-degree counterclockwise rotation, and little r is the reflection over the vertical line. Okay, so what is, in fact, n in this case? So it's generated by r squared, and that is the 180-degree rotation. So because this is a square, so if you do the 90-degree rotation twice, that's the 181. So n is just going to consist of the identity and then r squared itself. So no matter how many times you do that r squared rotation, it's either just the identity or it's r squared again. Okay, so what are going to be the cosets in this case? Okay, so let's see if we can list them. So I'm going to have n, of course, and n is I and then r squared, so that's n. Okay, and then if I multiply another group element by those two things that are in n, like for example, if I multiply little r on the left of those, then what do I get? So I would get little r, and then I would get little r squared. Okay, so this will be little r n. And then if I multiply some other group element that I haven't seen yet, like maybe capital R by itself. So if I multiply capital R by both of the elements in n, then I'm going to get capital R and then capital R cubed. So that will be this one, Rn, like that. And then what are the last two that I haven't seen yet? So I think I haven't seen little r squared, and I haven't seen, or no, I did see that one, didn't I? I haven't seen this one. And I also haven't seen little r big R, like that. So I think this one will be little r big R times n. And that is my 4 cosets. So let's see if we can put them into a table. So this will be multiplication this time. So it'll be n, and then little r n, and then capital R n, and then little r big R n. Okay, and on the other side, the same thing. It's a little bit sloppy, but oh well. Okay, so let's see what we get here. So n is always the identity coset. So when you're filling in that row and column, you can just copy it down. So I'm just copying these from the side because this is the identity row and column. Okay, now let's try the tricky ones. So first of all, I've got Rn times Rn. So the way this coset operation works is you multiply the two little elements together. So this is little r times n. So little r times little r, that is a reflection. So a reflection is always its own inverse. So this is just going to be n again. And then here I've got little r n times big Rn. So that's going to be little r big Rn. And that is one of my elements. So I'm going to leave that one like that. And then I've got big R n times little r n. Now this one is a little bit tricky because big R, little r, that is not one of my group elements. Or sorry, it's not one of my G mod n elements. That group is the one I meant. But I hope you remember that we can actually, one of the dihedral group rules is that, so in D4, oops, the 4 is down here. Little r times any r to any exponent, you can move the big R around the little r if you make the exponent negative, like this. So it's just like a random rule that we can use. So in this case, I'm able to move little r to the front and this big R here, and then capital R to the -1 is actually the same as oh shoot, which one is this going to be? So it's going to be r cubed. And then, sorry, I'm sort of running out of space here, but maybe I can make this a little like that. R cubed is actually one of the elements of r, oops, okay, it's one of the elements of this one. Because this is r cubed right here, that's an element of little r big R n. So I hope that explanation made sense to you. Sorry, it's a little squished in there. Right, so let's keep going. So then we do little r big R n times little r n. So this one is going to be, maybe I need to squish a little more up here. So this will be little r big R little r n, and then we can do the same process that I was just telling you about, where you can move the capital R around if you make its exponent negative. So that'll be like that, and then that will be, the two little r's are going to cancel out, so that's just going to leave you with that one, and then this is the same as r cubed, because doing the, how can I say it, like the inverse of capital R is clockwise rotation by 90 degrees, and that's the same as doing counterclockwise rotation by 270 degrees. So anyway, r cubed is one of the elements that is in Rn. Okay, so r cubed is right here. So that will be the same coset as capital Rn. Okay, so I'm getting a little squished in this table here. I probably should have left myself more room. But anyway, I hope the next one here won't be as squishy. So this will be Rn, like that, and then that'll be r squared n. And then r squared is one of the elements of n, so this will actually just be n. Okay, and then the next one, so this will be little r big R n times big Rn, so this will be little r squared n. And then let's see, where is little r times r squared? That one is in this coset, little Rn. Okay, and then little Rn times little r capital Rn. So those two little r's are going to cancel each other out because little r is its own inverse. So this is just capital Rn. All right, and then I think at this point we can finish by Sudoku rules. So let me go ahead and do that. So which one did I not hit in this row here? I think I didn't get little Rn yet. And then that leaves me, for this row and this column by Sudoku rules, that leaves me just n down there. Okay, sorry it's a little squishy here. But anyway, that's how you do it. Okay, so now that we've learned about quotient groups and what they are, and we've gotten a little practice under our belt with them, let's talk about how we can actually use these things. So I want you to remember that the order of G mod n, which is the number of cosets of n in G, is denoted with this notation right here. and that's also called the index of n in G. And remember also that whenever the order of G and the order of n are finite, that the number of cosets is just going to be the number of elements in G divided by the number of elements in n. But do keep in mind that this order right here, the number of elements in the quotient group, that can actually be finite even when G and n themselves are not finite. So we saw that in part B of the last activity. We had Z and then the subgroup of Z generated by 5. Neither of those was finite, but the quotient group was still finite. It had 5 elements. So quotient groups, they are actually extremely useful as well as being pretty fun. Often we can more easily prove things about G mod n than we can about G. And whenever we find out by looking at G mod n may actually tell us something about G. So investigating G mod n to find out things about G, that is a really standard technique in algebra, and we're going to do some of that ourselves, starting with this next theorem here. So the following theorem is an example of the sort of things we can find out about G by investigating G mod n. So remember that Z of G, that is the center of G, and that's the subgroup of all elements that commute with everything in G. So in other words, Z of G is this. It's all of the elements A in G, such that AB equals BA for all B in G. So like I said, that's the elements that commute with everything in G. So this theorem here, theorem 27.10, it says if G is a group and G mod ZG is cyclic, then G is abelian. So that's quite interesting, and you could imagine how it might potentially be easier to prove that G mod ZG is cyclic than it would be to prove that G is abelian. So this could be useful in those circumstances. Okay, so let's look at the proof of theorem 27.10, and I just put the theorem up there in the corner for you to look at. Okay, so proof, let G be a group such that G mod ZG is cyclic, and let us call n, so we're calling ZG just by the name n. So then since G mod n is cyclic, that means there must be some element in G mod n, and we're going to call that element Gn, that generates G mod n. In other words, we're saying that G mod n is equal to the cyclic group generated by the coset Gn. So to show that G is abelian, we need to show that AB equals BA for all AB in G. That's what it means to be abelian. Okay, so let's go ahead and try it. So let A and B be elements of G. Then that means that AN and BN, those are going to be cosets, so those will be in G mod n. And then moreover, since G mod n is generated by the coset Gn, that means that AN must be some power of Gn. So AN is equal to Gn to the k, and then that will be G to the k n. And then likewise, we can say that Bn, since G mod n is cyclic, this must be some power of the generator. So it's the mth power, let's say, of the coset Gn. So Bn is going to equal Gn to the m, and then that will also equal G to the mn. And then this will be true just for some integers, k and m. We don't know what they are, so we're just calling them k and m. Okay, so with all this done, now we can say that since A is an element of AN, and since AN is equal to G to the KN, that means that A must be equal to G to the K times NA for some element NA in N. That's what it means for A to be an element of AN. And then likewise, we can do the same thing for B. So since B is an element of Bn, and Bn is equal to this, it's equal to G to the mn, that means that B must be equal to G to the m times NB for some element NB of N. Okay, so with all that done, it's now pretty straightforward to show that AB equals BA. You just have to use the commutative properties of elements that are in, because remember N is the center of G, so everything in N commutes with everything in G. Okay, so what we're going to do is we're going to start off by saying AB equals, and then we're going to replace A and B with these equations that we found for them. And then since NA and NB are in the center of G, that means they commute with anything here. So we can rearrange and we can put NB at the front and we can put NA at the back. And then notice we haven't changed the order of GK and GM, but actually you can change the order of those two, because whenever you have a single element to some different powers, those different powers of that element will commute with each other, because you could always just write out G to the K times G to the M as just like a really long string of G's. Right? And then you can break that up however you want. So you can also write that g to the k, g to the m is the same as g to the m, g to the k, by just stringing out all those g's and then grouping them differently. Okay, and then again, using the commutativity of NA and NB, we can then rearrange just a little bit more and pop NB into the second position here. And then what you've got is you've actually got BA. Okay, so you started with AB and you get BA. And that is the proof. Okay, so this is the last thing that I want to look at today, and we're going to work on proving this next time. So we're still pretty far from the end of investigation 27, but I think we do need to stop after this today because it's getting a little long. So this is Cauchy's theorem for finite abelian groups. Understanding the subgroups of a group is important to understanding the group. Lagrange's theorem gave us a necessary condition for a subgroup to exist, but it did not give us a sufficient condition for existence. So remember that in Lagrange's theorem, that told us that every subgroup of a group, the order of the subgroup must divide the order of the group. So that was a necessary condition. In other words, you cannot be a subgroup unless your order divides the order of the group. It's necessary that your order divides the order of the group, but it doesn't give us a sufficient condition, so it didn't actually tell us much about when subgroups do exist. We did find out one little thing as a corollary. We found out that there must be at least one subgroup of prime order that divides the group order, but we don't know which prime divisor that would be. So that wasn't really that helpful. But this Cauchy's theorem, this will actually tell us that there must in fact be at least one subgroup of order P for each prime divisor of the group order. But keep in mind though that this is not for all groups, this is only for finite abelian groups. So it's a limited result, but it's pretty useful anyway. So theorem 27.11, let's just read it. Cauchy's theorem for finite abelian groups. Let G be an abelian group of finite order n. If P is a prime divisor of n, then G contains an element of order P. And so, of course, if G contains an element of order P, then there will be a subgroup also of order P that will be generated by that element. Okay, so I think that's all we have time for today. So if any of you are having trouble on your homework or your test or anything else, please send me an email, and otherwise, I'll see you next time.